begin with a recap of the concept of motion of center of mass and linear momentum of a system of particles before we come to momentum conservation examples. Okay, so the motion of a center of mass for a system can be described by the following parameters, as we have seen before. Displacement of the center of mass is given by summation of mass into displacement for individual particles divided by the total mass. Similarly, velocity of center of mass is again summation of mass into velocity divided by total mass. And similarly, acceleration of center of mass is summation of mass into acceleration for individual particles or individual masses in the system divided by the total mass. So note that all these formulae basically come from the basic definition that position of center of mass was defined as summation mr divided by summation m. So by applying the relationship between displacement and position, that displacement is change in position, okay, or velocity is rate of change of position with respect to time, and acceleration is rate of change of velocity with respect to time. So by applying these kinematical definitions, okay, to this fundamental definition of position, that's how we came up with these three relations: position, velocity, and displacement of the center of mass. Okay. Now, just before we go ahead, one thing, there is statistically now we give this kind of expression a special name. The summation m into any parameter, let's say x, okay, divided by summation m. In statistics, this parameter or this calculation, okay, it is called the weighted mean. It's called the weighted mean value of whatever parameter x. Okay, just like summation x divided by total number, this is called the mean value of x. Okay. So basically, x1 plus x2 plus like that going up to xn divided by the total number of terms, okay, that is called the mean value. Now similarly, this term over here, okay, which is basically what it is equal to m1 x1 plus m2 x2, like this, the summation going up to the last term mn xn divided by the total mass, that is m1 plus m2 plus like that. Statistically, this term is called the weighted mean of x. Okay. So if we say in words, we can say that displacement of center of mass is the weighted mean displacement of all particles in the system. Okay. Similarly, velocity of center of mass, that is the weighted mean velocity. Okay. Similarly, acceleration of center of mass, it is the weighted mean acceleration. Okay. So that is the same thing as these equations that we have written on top, because this is the general meaning of the term weighted mean. Okay. So the term weighted mean, okay, in statistics is defined like this, whereas the term mean, again in statistics, is defined like this. So that is the difference between saying what is the average value or mean value of x and what is the weighted mean value of x. So weighted mean is summation of mx divided by summation m, whereas the mean value is summation x divided by the total number of terms.
Sir,
Yes.
so sir, do we need to write this again?
Sorry, come again, Meta. Bhargav, yes.
So sir, we need to write this again except for the right part.
No, you don't really need to write this. We have done this in the lecture uh, before the previous lecture. We have done the definition of displacement, velocity, position. Okay, just make sure that these ideas are clear to you and there's no doubt in any of these equations. Okay, then we can move forward. Okay.
Oh sir.
So are you clear with all these equations?
Yes sir. Like
Okay, familiar with them, clear with them. Okay. Then one more thing that we had seen, which was very important. Okay, moving forward. Second thing that we had seen, that this equation, that velocity of center of mass is summation mv or weighted mean of the individual velocities. This also means that we can define the momentum of our system, the linear momentum of the system, as total mass into velocity of center of mass, and that becomes summation of mv for all the particles. Okay, so this is how we define the momentum of the system, and that is equal to the summation of momenta of all the particles, where capital M is summation of mass for all the particles. So this is total mass. So we define linear momentum of a system as total mass into velocity of center of mass, and that is equal to the vector sum of the momenta of the individual particles. And further, when we differentiate this, we see that rate of change of momentum for the system becomes rate of change of individual momenta, okay, of the particles. So that becomes summation of rate of change of this, which is nothing but the summation of net force acting on the ith particle. So we had seen that when we see the summation of forces, okay, over all particles in the system, okay, then that equals to what? It equals to the net external force. Okay, because internal forces cancel in action reaction pairs. So that was a very critical concept that we had seen. So internal forces cancel in action reaction pairs. Okay. So this term therefore becomes equal to the net external force. So we have the equation that the net external force acting on a system equals to the rate of change of its linear momentum. Okay. Or that is equal to rate of change of total mass into velocity of center of mass. So that we can also write as mass into acceleration of center of mass, because total mass is constant. Okay, so this is the form of Newton's second law applied for a system of particles. For a system of particles. Okay. And then, of course, from this we understood that if the net external force is zero, that means the momentum should be constant. So that is the situation in which we apply conservation of linear momentum. So today's lecture, we are mostly going to focus on the applications of conservation of linear momentum, including collisions. So this is, like you can say, it's one of the most important aspects of mechanics. Okay, in your entire class 11th syllabus, this is one of the most important aspects of mechanics, which is the conservation of linear momentum applications. Okay, so further what we understand is that therefore, if the net external force, okay, on a system is 0, then rate of change of momentum is 0, which means that the momentum is constant. Okay. So when the net external force is 0, that is when the momentum is constant, or we say it is conserved. Anything that is constant, we can say it is conserved. Okay, so we had seen some examples of that in the previous lecture. So let's continue ahead with some more examples today. Actually, we had seen a couple of examples of this in the last lecture, not in the previous lecture. Okay, because previous lecture we were back to position of center of mass examples. So let's come back to this conservation of linear momentum examples. All right, so let's look at an example of this. So now we have something like this. On a frictionless surface, okay, we have two blocks which are connected by a spring. Okay, and initially the spring is in a slightly compressed state because we are applying some force to balance it. So on a smooth surface, we have two blocks of mass m1 and m2 connected by a spring. Now, initially they are at rest, both the blocks, but also initially the spring is in a compressed state. So it's not at natural length, it is at L minus x naught because of some external force that we are applying. Okay, but equal and opposite external force. Okay, so equal and opposite forces, okay, keep the above system at rest with the spring compressed by x naught equal to, let us say, 2 centimeters. Okay. Also given that m1 is equal to 3 kilograms, m2 is equal to, or let's make m1 the larger one. So m1 is 6 kilograms and m2 is equal to 3 kilograms. And the spring constant is 25 newtons per centimeter. Okay. So this is the initial state. So equal and opposite forces keep the above system at rest with the spring compressed by this much initially. Okay. Now, suddenly, both forces of magnitude f each are simultaneously withdrawn. Okay. So what will happen the moment we withdraw these forces? Can you tell me what will happen to the system? At the moment when we withdraw the force, what is the state of the spring? It is compressed, no? So will the system start moving or will it remain at rest?
So it will start moving.
How it will start moving? Both the blocks will be pushed by the springs, right?
Yes, sir.
So this will develop some acceleration like this. This will develop some acceleration like this. A1 and A2. Okay, this is just after. Okay, this is just after.
Sir, this will happen when it is compressed, no?
Yeah, see, it's compressed initially now with the force applied. Now, the moment I release the force the blocks will accelerate, no? Because earlier when I was applying the
Yes.
force, obviously it was balancing the spring force. But जैसे ही मैंने दोनों force को withdraw कर दिया है, both the blocks will start accelerating because the spring is in compressed state. Okay, so the spring is applying a tension like this. Whereas earlier when I was applying this force, the spring was still applying a tension, but the net force on the blocks was zero. No? Why? Because F was balancing that. So earlier what was happening, before I withdrew these forces, this tension was still there. Okay, but this was at rest. This was not accelerating. Why? Because F was balancing T, which was equal to Kx naught. This is initially, but the moment I withdraw the forces, now these will start accelerating because that F is gone. Okay, so just after F is released, this is the situation. Okay, so first of all, we have to find the accelerations A1 and A2 at the instant just when F forces are withdrawn. Okay, so that is more like a Newton's law problem. Actually, we'll discuss next. Okay, now the second part is where our center of mass concept will come in. We have to find the speeds of the block, speeds v1 and v2 at an instant later. Okay, when the spring is at natural length or it's relaxed. Okay. Initially the spring is compressed, so from where I'm releasing the system, the spring is going from a compressed state, but by the time the spring relaxes back to natural length, the two blocks would have picked up some momentum because of the force that the spring is continuously applying on them in the opposite directions. Okay, or each block would have gained some kinetic energy because the spring would have released its potential energy. So how much is the individual speed of each of the blocks? We have to find in meters per second, and the first answer we have to find in meters per second square. Okay. So the hint to you is, for the first part, make free body diagrams. It's about acceleration. Okay, to solve Newton's second law for each block. Okay. So solve that equation that the net force acting on each block is mass into its acceleration. So from that you find out the acceleration. But for the second part, you will see that as the spring relaxes, okay, from the compressed state L minus x naught to L, to natural length L, what happens? The blocks are pushed by variable spring force. Okay, variable tension T is equal to Kx. So there's no point using Newton's law. So instead what you do is use work energy, okay, and use center of mass concept. So what we mean by the center of mass concept, I'm going to discuss in a moment. Okay, so start with the first part. Just tell me how much the answer should be in the first part. All the data is given to you in the question, so just try it out.
Sir,
Yes.
sir, this Sunday our test is there of system of particles. So
Yeah.
our chapter is not done. So how
It
much?
will be only up to conservation of momentum. What we are doing today now. So before that, I have one more lecture this week, and that also I'll be doing some revision questions. So you'll be prepared for the DPT. Okay.
Okay, sir.
Okay.
Okay, sir. Thank you.
Right. Okay. So anybody got the answer for the first part? What are the accelerations? You made the free body diagrams. So at the moment when we release the system now, what is the state of the spring? We just discussed the spring as a compression of 2 centimeters. Okay. So the spring is pushing both the blocks on either side with a tension. Okay. It's pushing with a tension outwards like this. And this tension is equal to kx naught. So that is 25 newtons per centimeter into 2 centimeters. So the tension equal to kx naught is equal to 50 newtons on each block. Okay. So they will have an individual acceleration in this direction and in this direction. Okay. Which will be equal to how much? E1 will be equal to T upon M1. So that will be 50 by 6 or 25 by 3 or 8.67 meters per second square. Whereas A2 will be T by M2 or 50 by 3. So that will be this is 8.33. This is 16.67 meters per second. So these will be the accelerations. Okay. Now notice one thing over here. What is the if we take the system as blocks M1 plus M2 plus the spring. Okay. Then for this system, what is the acceleration of the center of mass? It should be M1A1 plus M2A2 divided by the total mass. So notice here, if I write that in scalar form, it will be minus of M1 was how much? 6 kgs into A1, which is 25 by 3. Okay. Plus M2A2, which is plus 3 into 50 by 3. Okay. Divided by 6 plus 3. Why this is coming with a minus sign? Because the acceleration is in the negative direction. So in 1D form, I can write it as like this. Just a moment. So I can write this as 6 into minus 25 by 3. Okay. Because A1 is minus 25 by 3 I cap, if I take this as my x-axis, whereas A2 is plus 50 by 3 I cap. So in scalar notation, it will become like this. So as expected, what is the acceleration of the center of mass coming out to be? It's coming out to be 0. So acceleration of the center of mass will come out to be 0. Now, why this is expected? Because net external force on the system is equal to 0. Okay. To 0. Now, the tension in the spring is an internal force now, so it cannot give the center of mass any change in momentum. Okay. The individual blocks are accelerating, but they're accelerating in opposite directions in such a way that the center of mass will not accelerate. Therefore, what will happen? The center of mass will remain at rest. Okay. Because initially when they started, both of them started from rest now. Okay. This is just after the force, external force F is removed or withdrawn. Okay. Now, even when we were applying the external force, that time also the center of mass would have been at rest, because what would the net external force have been? It would have been 0. No? We are applying equal and opposite forces. So even in this case, when we are applying force in this way, but even right now, what is happening? The net external force is zero. Okay, because the two individual forces are cancelling each other. Okay. So the net external force is equal to plus Fi cap minus Fi cap is zero. Okay. So even at that point of time, the acceleration of the center of mass is zero. And of course, after we withdraw these two forces, the acceleration of the center of mass still remains zero. Okay, so hope this part is clear. Now let's move on to the second part. So for the second part, we'll have to compare the system from this initial moment, okay, when it just started moving with acceleration, to a later moment when it is having that kind of situation, that this spring has come back to natural length position. Okay, so let's say our initial state, I'm showing over here. So this distance is L minus x naught. So both the blocks are at rest right now, but they are having strong amount of accelerations, A1 and A2. Okay. Now after some time, when the spring comes back to natural length position, by then what has happened is the blocks have shifted by a certain amount. Okay, so let's say this block has shifted here. Okay, and this block has shifted somewhere here. It's a lighter block, so it will get pushed further away. So now say in this diagram, let's say the spring has come back to natural length. X is equal to 0. So what's happening is because of this tension continuously acting between this diagram and this diagram, now this has got some speed v1 and this has got some speed v2. Okay, but between here to here, what is happening? Initial velocity of center of mass is 0. Acceleration of center of mass is 0. So center of mass does not move. Initially, VCM is 0 and acceleration of the center of mass is 0 throughout. Okay, so that means that the center of mass does not move. So this is where the center of mass was initially. Then in the final diagram also, it's not moving. It's remaining at the same position. But while the center of mass is not moving, this block is moving by, let's say, x1, and this block is moving by x2. Okay. So what we can see is that since the center of mass remains at rest, so we can say that the displacement of the center of mass is 0. So that means minus m1 x1 plus m2 x2 should be equal to 0. Okay. And it also means that velocity of the center of mass is 0. So that means summation of, or that means basically vector sum of the momenta should be equal to 0. So which means in scalar equation, if I write minus m1 v1 plus m2 v2, this should be 0. So this is going to be the useful equation for us because we want to find out v1 and v2. So we'll write this as equation 1. And where this is coming from? This is coming from momentum conservation. This is coming from conservation of linear momentum for the system. When we write down this equation, we will get that V2 is equal to twice of V1, because M1 was 6 kilograms and M2 was 3 kilograms. Okay, but we have V1 and V2 two unknowns. No? So we need one more equation. So where that other equation will come from, that you can see that as the system is moving from here to here, note additionally another thing that is happening, that there is no external force, okay, or non-conservative force doing work. Okay, so that means also the mechanical energy of the system is conserved. That's where we'll get the second equation from, that for the system, the change in kinetic energy plus change in elastic potential energy of the spring should be zero. This is where a second equation will come from. This is conservation of mechanical energy for the system. Okay. Why? Because work done by external force is zero. There is no external force only. Work done by non-conservative force is zero. So change in kinetic energy plus change in potential energy is zero. Okay. So now I want to formulate this equation with the values and all, and then use the two equations 1 and 2 to solve for V1 and V2. Okay. So use all these values which I had given you, that K was equal to 25 newtons per centimeter. Okay. The initial compression x naught was 2 centimeters, and the masses are 6 kilograms and 3 kgs. So use these values in the two equations 1 and 2, formulate the equation 2, and then take help of equation 1, and from that solve for the individual values of V1 and V2 at the instant when the spring is back at the natural length. So just try this out. Okay. It seems like a lengthy process and quadratic equation and all, but it will not be. When you substitute the first equation in the second, you'll see it's quite an easy equation to solve. It's quite an easy equation to solve. Just try this out.
Sir, sir, can you scroll up? Hello, sir. Sir,
Okay, so anybody got the answer? Let's try to understand this.
Sir,
Yeah.
sir, I was telling that please scroll up.
Oh, scroll up. Okay. So for that, this part.
Yes, sir.
Okay. Okay. Note this down quickly, then start. So you can work out the second part also.
Sir, done.
Okay. Okay, now see, in solving this part, what you have to now do is basically you have to populate this equation, the second one. What is the change in kinetic energy going from the initial state to the final state? So you can see initially U is equal to 0 for both. Okay, so the initial kinetic energy is 0. Whereas in the final state, okay, the spring is relaxed, but the blocks are having speed V1 and V2. So the kinetic energy is half m1 v1 square plus half m2 v2 square. Okay. But also initially the spring is compressed. Okay, so the initial potential energy of the system is half k x naught square. Whereas in this situation, the spring is at natural length or at the relaxed position. So the final potential energy is 0. So now use these four values, initial and final potential energy, initial and final kinetic energy, to populate the terms of the second equation and solve equation 1 and 2 with the numerical values of m1, m2, k and all, and you can calculate for v1 and v2. And as I was saying, it's not as difficult to solve as it seems, because when you substitute from the first equation, you'll see it becomes a single equation of it becomes a simple equation of a single variable. You'll get v1 square is equal to something, or v2 square is equal to something. So you can just calculate v1 and v2 directly from that. Right. So anybody got the answers? Okay, so let's see what this second equation will become. The second equation, conservation of energy, will become half m1 v1 square plus half m2 v2 square. That's the change in kinetic energy, but minus half kx naught square. There's a change in potential energy, so that should be equal to 0. Okay. So when we substitute the values, this will become, you can cancel off the half throughout anyway. So you will have 6v1 square plus 3v2 square is equal to, half is anyway cancelled out, 25 into 10 raised power 2, because we'll have to convert this to SI unit, newtons per meter, okay, into x naught square. So x naught also you'll have to convert to meters. Okay. So 2 into 10 raised power minus 2 square. So we will get this, that 6v1 square plus 3v2 square is equal to, this will become 25 into 4, so that's 100. So this is, I think, going to become 1. Just check, because this is 25 into 10 raised power 2 into 4 into 10 raised power minus 4. Okay. Yeah, so it should become 1. Okay. So now you substitute this thing, that V2 is equal to twice of V1 in this. So V2 is equal to twice of V1. So we will have 6v1 square plus 3 times twice of v1 square is equal to unity. So 6 plus 12 is 18v1 square is equal to 1. So v1 will come out to be 1 upon square root 18, or 1 by 3 root 2 in meters per second. So that's your v1. Okay. 1 by 3 root 2 meters per second. And so your v2 will be twice of v1. So that will be 2 by 3 root 2, or root 2 by 3 meters per second. So v1 and v2. These are the answers.
Sir,
Yes.
sir, could you just zoom out to the calculation where you have done, because it's not readable.
You want me to this thing it, right? Magnify it a little. Is it
Yes, sir.
okay?
Where you have written down done that calculation. Yes, sir. Thank you.
Okay, this part. Okay. So all I've done is substituted m1, m2 over here and k. Okay. So we have substituted m1 as 3 kg, m2 as, sorry, m1 as 6 kg, m2 as 3 kg, and k as 2500, because just a minute, we have to substitute in SI unit, okay, not in CGS unit. Okay. So in this, we are substituting m1 as 6 kg, m2 as 3 kg, k as 25 into 10 raised power 2 newtons per meter, and x naught as 2 centimeters, so 2 into 10 raised power minus 2 meters. Okay. And then of course equation 1 earlier was giving us that v2 is equal to twice of v1. This is what we substituted. This is from equation 1 earlier. Okay, so just go through this carefully once. It should be quite simple after that, how you solve the equation. Okay, people, so done with this.
Yes, sir. Done.
Hmm. Okay. So let's. So this is like one very standard type of situation of the application of conservation of linear momentum. Now let's look at another situation. Conservation of linear momentum. Now in this next example, suppose, now I think we had done this type of question, one of them earlier that day. So I'll pick up a slightly more complex type of question, the same concept. So we have a smooth surface, okay, on which we have a wooden platform. Okay, on which we have two people standing at the two ends of the platform. We would have done a question where a single person was at one end. So let's say these are two people, A and B, okay, and this is a wooden platform. So mass of the person A is 60 kilograms. The mass of the person B is 40 kilograms. And the platform, it has mass M equal to, let us say, 50 kgs, okay, and a length L equal to, let us say, 12 meters. Okay. Now this is a perfectly smooth surface, whereas the surface of the platform is rough because otherwise the people would not be able to walk. Okay, so initially the system is at rest as shown. Okay. Now what happens is A and B start walking. On the platform slowly, okay, and eventually stop to meet at its midpoint. So at the platform's midpoint, A and B finally stop and meet. Okay. So during this displacement, we have to find out what is the displacement of the center of mass for A plus B plus the platform as a system. Okay. During this time. Okay, and we have to calculate how much does the platform displace. Okay, and we have to calculate A and B's individual displacements. And when we say individual displacements, we mean with respect to ground frame. With respect to the ground frame. Okay, so just try and work out this question, people. If you understand the answer to the first part correctly now, with the proper logic, then you will see that it's just a matter of fitting the equations for the second and third part. Okay, so try to, now the first part's answer is actually quite logical. There's not too much calculation involved in that. It's quite logical. So think carefully about the first part's answer and send me on the text message. I'll tell you whether you're right or not. Okay? Yeah, so no, so unfortunately now people haven't got the first thing right. Okay. See, if you take the whole thing as a system, is there any net external force? As the two people are walking on the platform, is there any net external force that acts on the system? Just think of that thing carefully first. See, just before they start moving, what is the state of the system? It's at rest. At rest. So velocity of the center of mass is 0 at this point of time. So momentum of the system is 0 at this point of time. Okay. So the center of mass will be where? This guy is 60 kgs. Okay. This guy is 40 kgs. Okay. And the center of the platform, that's where its mass is located. You can say its center of mass is here. So the center of mass of the system should be somewhere here, closer to the 60 kg guy. This is where the center of mass of the system should be. This is the center of mass for A plus B plus the platform. Now what happens when A starts moving? In order to propel himself, he applies some backward force on the platform, and his feet experience equal and opposite forward force. So he gains a forward acceleration. Okay. B applies a backward force on the platform like this. So he attains a forward acceleration like this. Okay. And because of that now, okay, so because of that now, let us say that the system, the platform also, let's assume it gains some acceleration in this direction. This is the acceleration of the platform. The platform starts slipping on the floor. Okay. But you will see that the net external force on the system is how much? It's 0. Net external force on the system is equal to 0. So acceleration of center of mass should be 0. Momentum of the system is conserved, and how much is equal to? It is equal to 0, because initially it was equal to 0. This was initially, but even later the momentum of the system will remain 0. So velocity of the center of mass will remain 0. So displacement of the center of mass will be how much? 0. So that is why the answer to the second part, to the first part, is that it will be 0. The displacement of the center of mass will be 0, because the momentum of the system is 0 throughout. Okay. So this is the first thing you have to understand about the question. Once you understand this point, rest is quite easy to understand. That what will happen is that, let's say we had understood that initially this is how the system was looking like. So we had A here, we had B here. Center of the platform here was 50 kg. Okay. So the center of mass of the system must have been somewhere here, closer to A. Okay. This was the situation at t equal to 0. Now after A and B have walked, okay, what has happened? The platform would have moved in such a way that wherever the platform center is, that is where they meet now. But that is where the center of mass of the system is also now. So they meet at the center of the platform. but that should coincide with the center of mass, because the center of mass should not have moved. So now A, B and the center of the platform are at the same position, but the center of mass itself has not moved. So this is still where the center of mass is. So if I overlap this diagram on top of this diagram, okay, this is the final situation. So if I overlap the final situation on the first diagram, the center of mass should exactly coincide. Okay, so going from here to here, the center of mass has not displaced. Okay, but in the new position, where is the center of mass? The center of mass is now at the midpoint C of the platform. Okay, because A and B are both at that point C only. Okay. Whereas in this diagram, where was the center of mass? In the initial situation, the center of mass was somewhere between the left end where A is standing, A's position, okay, and midpoint. Okay, because mass of A is greater than mass of B, so the center of mass, okay. But between this and this, the center of mass is not moved. So from this, can you tell me what is the displacement of the Planck? What is A's displacement? And what is displacement of B with respect to ground?
Sir, Planck means?
Displacement of the Planck. Now the Planck has shifted backwards. See, this is what is happening now. Initially, A was here, B was here, and the Planck center was here, and the system center of mass was here. Okay, but now in the final position, while A has moved from here to the center of the Planck would have shifted backwards now, because A is the heavier mass. So the Planck would have shifted like this from here to here. This is the displacement of the Planck. Okay, and E would have moved to the center of the Planck. B would have moved to the center of the Planck. So in the final diagram, the center of the Planck is here. Okay, so now we can see that A has actually traveled in the ground frame only this much. This is the displacement of A. He has not traveled 6 meters. This is half the length of the Planck. He has traveled less than 6 meters. Whereas B, on the other hand, in the ground frame, has shifted more than 6 meters. Because the Planck itself has shifted back like this. Okay. Now the length of the Planck is given to us as 12 meters. Remember that. Is the concept clear now?
Yes, sir.
Okay. So work it out quickly now. So we will have to use this fact from the first part, that the displacement of the center of mass of the system should be 0. So make use of this. And the other thing we will have to make use of is that displacement of A with respect to the Planck. And the Planck's frame A is going how much? He's going half the length of the Planck forward. So he's going plus 6 in, or you can say the displacement of A in the Planck's frame is 6 I cap, taking this as the x-axis. But displacement of B in the Planck's frame is how much? It's minus 6, or in vector form, we can say that with respect to the Planck, B has moved 6 meters backwards. Okay, because the length of the Planck was 12 meters. So now see how we can fit in the center of mass equations along with this to get the values of SA, SP, and S of the Planck individually. Okay, we know these two facts, that the displacement of the center of mass should be 0. And we know these two facts, that the displacement of A with respect to the Planck should be this much. The displacement of B with respect to the Planck should be this much. Okay, so there are two ways of doing this question. One is like strictly using equations and not using the diagram in any way. It's like a non-intuitive way. Okay, so one is that, we just just a minute, people. One method is that we can do this question just blindly. Okay, just using the facts and the equations. Okay, so we can say that, okay, the person A has some displacement SA, which we don't know. The person B has some displacement SB, which we don't know. The Planck has some displacement SP in the ground frame, which we don't know. But what are the facts that we do know? We know that the displacement of the center of mass is 0. Okay, and we know that with respect to the Planck, A is having a displacement of +6, and with respect to the Planck, B is having a displacement of -6. Okay, so you can see that from this we will generate 3 equations. Okay, and we have the 3 unknowns, so we should be able to solve that. So that is one way of solving. Okay, so it corresponds to the diagram I've made above, but I will not be substituting anything from the diagram directly. I'll just be substituting in the concepts. So equation 1 will tell me that displacement of center of mass is 0. That means summation of mass into S should be 0 for the system. So this is 3 things in the system. So mass of A into displacement of A plus mass of B into displacement of B plus mass of the Planck into displacement of the Planck should be 0. So this equation will become 60 SA plus 40 SB plus 50 SP will be 0. I'm not substituting anything with plus minus because the answer will take care of which displacement is in the positive direction and which is in the negative direction. The only place where I'm substituting with plus minus is here, because that is corresponding to the fact that A in the Planck's frame is moving from here to here, and B in the Planck's frame is moving from here to here. So with respect to the Planck, this is B's displacement. So it's negative. With respect to the Planck, this is A's displacement. So this is the only fact with the direction which I'm making use of. So that's why here and here the relative displacements are coming with the proper sign, because the direction is also important. So this is giving me a simpler equation that 6 SA plus 4 SB plus 5 times SP should be 0. That is my equation 1. Okay. Now from the second thing, I'm getting displacement of A with respect to the Planck should be +6. So that means SA minus SP should be equal to +6. Okay. So that's the second equation. Okay. And from the third aspect, that the relative displacement of B with respect to the Planck is 6, but in the negative direction. So I should, whatever the value of SP and SP, it should be such that the difference of these two is equal to -6. That is my third equation. So now what I will do is I'll substitute these two in this. Okay. So that will tell me 6 times SA, which is 6 plus SP. Okay. So this will give me SA is equal to 6 plus S of the Planck. This will tell me that SP is equal to -6 plus S of the Planck. Okay. So 6 times SA plus 4 times SP, okay, plus 5 times SP should be 0. So 36 plus 6 SP minus 24 plus 4 SP plus 5 SP should be 0. So let's see what this gives us. 6 plus 4, 10 plus 5, 15 SP should be equal to, take these terms on the other side. So 24 minus 36 or 15 SP should be equal to minus of how much? 12. So the displacement of the Planck is minus 12 by 15 or minus 3 by 5 or minus 0.6 meters. So that means the Planck is shifting back by 6 meters. Now if you go back to the diagram, you can see the minus sign makes sense, because in this diagram, what is the displacement of the Planck? This is the displacement of the Planck. So it was expectedly coming as a negative quantity. So it's no surprise that the displacement of the Planck has come out to be a negative quantity. Any of these three will give you the same quantity, which is the displacement of the Planck. Whereas expectedly, what should be the displacement of A in the ground frame? It should be a positive quantity, but such that its magnitude is less than 6. So we are expecting SA should come out to be plus of something less than 6. And what should be the displacement of B? It should come out to be negative of something, but whose magnitude is greater than 6. So now you solve for the other two, and you'll see you'll get those also. That is obvious, because all we have to do is substitute back in the equation. So we've got, okay, this is this much. Oh, sorry, this is minus 0.8, my mistake, not 0.6. 12 by 15 is 4 by 5. That is minus 0.8 meters. Okay. So now from this we should get SA. Now see what was SA? SA was 6 plus SP. So it will come 6 minus 0.8. So that will become plus of 5.2 meters. So as expected, it's positive, but less than 6 in magnitude. Whereas SP will come out to be minus 6 plus SP. So that is minus 6 minus 0.8. So it's minus of 6.8. So A has actually traveled, B has traveled a distance more than 6.6 meters, but in the negative direction. Okay. So this is also quite a direct and intuitive way of solving the problem. Okay. But we have still not, really used the information that we got in the diagram earlier. If we had used that, then it could be like a little bit faster, a little bit easier to solve. So that's what we look at in the next situation. So you can say that this is method 1 of solving it by equations. By equations involving these three terms. The displacement of center of mass is 0. The relative displacement of A and B with respect to the Planck are 6 and minus 6 respectively.
Sir,
Yes.
sir, I have not understood that how the platform is going back.
Okay, so tell me something, that if we have a frictionless floor on which we have a platform like this, and there's a person standing on this. Now, if the person starts walking forward, what will happen to the Planck?
It will move backwards.
It will move backwards. Okay. Now, similarly, we had a situation where there's a person on the other side, okay, and he moves in towards the left. So what will happen to the platform now? It will move towards the right.
Yes, sir.
Okay. Now, in this question, what is happening? Both of them are there. Okay. So it's a question of who's going to dominate. So the answer to that is who has more mass. He will be the dominative factor. No?
Yes, sir.
So A ka mass 60 tha. So if A is walking ahead at a certain pace, that will give the platform a backward motion of that certain pace. B's mass is only 40 kg, so it's less. So even if B is walking at that same pace, the platform will go forward at a lesser pace because of that. Because A's mass is more. So that is why ultimately the platform is ending up going backwards.
Okay, sir. Now understood, sir.
And suppose you had just interchanged the masses of A and B, then when you solve these equations, you would have got the displacement of the platform instead as plus 0.8. And in that case, A's displacement would have been plus 6.8 and B's would have been minus 5.2, because the whole thing is like a mirror image of this. So the final answers, the sign of the answers will take care of the fact that which one is dominating. So actually in which direction the platform ends up sliding. Okay, now let's see a direct geometrical way of solving this situation. So that is of course dependent on the fact that we have understood beforehand that the 60 kg person's mass is dominating over the 40 kg guy's mass. So the platform is shifting backwards. So once we have made a guess about that, then we can use the geometrical relation over here. So method 2, if we are solving it geometrically using the fact that the center of mass does not move. So we use the fact that the center of mass is at rest. Okay. We just make a comparison of the two situations. Initially like this. Okay, the center of the platform, let's say here, and I'll just make a bit of an exaggerated diagram so that it's somewhat easier to show the. So I'm assuming that the platform is moving by quite a large distance. So the center of the platform has moved here now. So you can see that this is the displacement of the platform. This is the same thing as this one. Which is the same thing as this one. Okay. So if this has a magnitude of SP, okay. Now, where are A and B located in this diagram now? They have both met at the center only. Okay. So wherever the original center of mass was, now the new center of mass is at the same position. The center of mass is not shifted. So we are using this fact that the center of mass is not shifted. Okay. So ultimately what we have to do is, if we can find out this distance, the distance of the center of mass from the point C, that is the displacement of the Planck. Okay. So the displacement of the Planck has a magnitude which is equal to what? The distance of the midpoint of the Planck from center of mass initially. You see in the diagram, that's what it is. This distance, this is only the same as this distance. So you have to calculate that. And once you got that, now you can see that E's displacement in the ground frame is this. Okay. Now, again in the ground frame, or E's displacement is therefore equal to how much? This total distance is L by 2, half the length of the Planck. And this total distance is L by 2. Okay. So individually A and B's displacements, you can write in terms of L by 2 and this distance. Okay. So the magnitude of A's displacement will be equal to the length, half the length of the Planck minus the displacement of the center of mass. Sorry, displacement of the Planck. And B's displacement's magnitude will be L by 2 plus mod of S, okay, which you can see is this. So let us say, so now the only thing remaining is to find this. So how we can find this now? That's very easy. Let's just make ourselves a new diagram where this midpoint is our origin and this is our x-axis. So B's position here is at x equal to plus L by 2 or plus 6. Okay. The position of the Planck is at x equal to 0 and A's position is at x equal to minus L by 2 or minus 6. So then we can find out the position of the center of mass of the system. And then whatever this distance is, suppose this distance is D, you can see that's the same distance D over here. So magnitude of this distance is this D. Okay. So in this diagram, we have to just find the position of the center of mass. It is MAXA plus MBXB plus mass of the Planck into the position of the Planck, center of mass, divided by total mass. And you'll see once we have calculated this, the rest of the things are already done. It's very easy to calculate. Okay. So we can see that this Xcm is 60 into minus 6, okay, plus 40 into plus 6, okay, plus 50 into 0, because that's what we've taken as the origin, divided by 60 plus 40 plus 50. So it is minus 360 plus 240 divided by 150. You can see that it is minus 12 by 15 or minus 0.8 meters. So this is the position of the center of mass of the system with respect to the center of the Planck initially. This thing is that one. Okay. So D is equal to 0.8 meters. Okay. So therefore we can see that the displacement of the Planck has a magnitude of 0.8 meters. And from the diagram we can see its direction is backward. So it's minus 0.8 meters. We can see that the magnitude of A's displacement is L by 2 minus D. So that means that's equal to 5.2 meters. Okay. And with sign is becoming plus 5.2 meters. And the magnitude of B's displacement is L by 2 plus D. So that is 6.8 meters, but it's backwards we can see. So the displacement of B is equal to minus 6.8. So basically all we had to do in this question is we had to find the position of the system center of mass with respect to the midpoint of the Planck. And once we do that, we understand that in the second situation, A, B, and the midpoint of the Planck, all three of them coincide at the center of mass position. So obviously the displacements are easy to calculate from that distance D.
Sir,
Yes.
sir, can you tell that what is Xcm?
Xcm is the position of the center of mass with respect to this origin. I've taken this as my system now. So this is the position of the center of mass, okay, with respect to O, which is basically what? It is the midpoint of the Planck. Understood now? No?
Yes, sir.
Now I've taken my X axis along the length of the Planck with the origin of my X axis at the midpoint. So with respect to that origin, whatever Xcm I'm calculating is nothing but the position of the center of mass with respect to the midpoint of the Planck. Now, why I selected the midpoint of the Planck as my origin? Because that's what I needed to calculate. Now, I needed to calculate the distance of this midpoint of the Planck from the center of mass. So that is nothing but the distance between the position where the center of mass is located with respect to midpoint of the Planck. Okay, so for that I took the origin as the midpoint of the Planck and just calculated the x coordinate of the center of mass. So the magnitude of that x coordinate only becomes that distance.
Done, sir.
Done now?
Yes, sir.
Okay. Okay, next example we'll see of application of concept of center of mass is, let's say we have a situation like this now. This is like a smooth curve that eventually becomes a straight line over here. Okay. So this is some, like a block of wood which we have carved into a shape like this. And this is lying on a frictionless surface. So this is a smooth surface. This is a wedge of mass capital M, let's say. This surface is also smooth. So the three-dimensional diagram of this wedge would look something like this. You've carved this out of a solid block of wood into a shape like this. So it's this kind of a shape. With a smooth face over here, I guess. This is on the ground. Okay, now what we do is we take a small particle kind of object and release it from this position such that, so we just place it against the surface of the wedge and release it such that this height is h. Okay. So you just take that particle and place it somewhere here at the midpoint and release it from there. So it comes slipping down like this. Okay. So a particle P of mass, let us say MP, which is equal to capital M by 4. It's 1/4 the mass of the wedge, is released on the surface of the wedge, okay, as shown. So it is gently released from that position. Okay. Gently released on the surface as shown. Okay. Now what happens is, after a while, it comes sliding down. So when we release it, the system is at rest like this. But as it comes sliding down, we'll be applying a backward force on this now. So at some point of time, when the particle is here, it's moving like this, but the wedge is moving like this because of the interactive force. And because the particle is applying a force like this, and the wedge is applying an equal and opposite force like this, plus weights and all are acting. So this is like a normal contact force which is acting between them. So as a result of that, after some time, what we observe is that the particle has come to this horizontal part over here. It's about to lose contact with the wedge. So at that instant, let us say the particle's velocity is VA and the wedge's velocity is VB. So given that h is equal to 20 meters, okay, and g is equal to 10 meters per second square, we want to find VA and VB at an instant when the particle is at the other end of the wedge. It's about to slip off the wedge. Okay, so the key to solving this problem actually lies in this diagram over here. Try to understand how we can use conservation of momentum from this. Okay, and what else we can use, because all the surfaces are smooth. Okay, so take down the diagram of the question and just try to figure out what conservation principles we can use. Okay, to figure out what conservation principles, you can send me a text message also, and I'll confirm what you're thinking is right. Then you can try solving the problem. Okay, so let's work this out quickly. So you can see from this diagram that at any instant when the particle is sliding down the wedge like this, so if it's at a position like this, the mutual normal contact force which is acting like this between them, this is an action reaction pair, it cancels out. Whereas the external forces which are acting on the system, they are like this. The weight of this one, the weight of the Planck or the wedge capital Mg, and some normal reaction from the ground n prime. So you can see that external forces, okay, for the system, we are taking the particle plus the wedge as our system. So for that system, the external forces, the weight of the particle, the weight of the wedge, and the normal reaction from the ground, they are all vertical. Okay, so therefore, horizontal momentum for the system should be conserved and equal to 0. This is coming from horizontal momentum conservation. For the system. And the initial momentum was 0. So the initial horizontal momentum was 0. Okay. So we will apply that to now this situation. So in this situation, what is happening? The horizontal momentum Px for the system, it should be 0. So that means mass of the particle into VA with a plus sign minus mass of the wedge into VB, that should be 0. So that's our first equation, momentum conservation. So now it was given to us that the mass of the particle was 1/4 of the mass of the wedge. That means VA is equal to 4 times VB. So that's the first thing. Okay, and the other thing is there's no friction, so mechanical energy is conserved. So second thing, no friction. So work done by non-conservative force is 0, and work done by external force is 0, because gravity we'll take as an internal conservative force for the system. So we'll see that change in kinetic energy plus change in gravitational potential energy for the system should be 0. So this is conservation of mechanical energy. This was conservation of linear momentum or horizontal linear momentum. And this is now conservation of mechanical energy. So conservation of mechanical energy will tell us that half m into VA square for the particle plus half capital M into VB square for the wedge minus mgh, because the particle is dropping through a height of h. This should be 0. So again, in this substitute, mass of the wedge is 4 times the mass of the particle, and substitute VB, or rather VA, as 4 times VB, or substitute VB as VA by 4. Okay, so let's substitute that here. So capital M will substitute as 1/4 of the mass of the particle. Oh, sorry, 4 times the mass of the particle. Okay, but VB will substitute as VA by 4, and that should be equal to mgh for the particle. So M also cancels out now, and we get half VA square 1 plus 1 by 4 from here should be equal to GH over there. So VA should just come out to be square root of 8 by 5 GH. Okay, and VB is obviously VA by 4. So the important thing here is the conservation principles. So the two conservation principles we are able to apply to this system here are horizontal momentum conservation and conservation of mechanical energy. So this is the first thing, and this is the second. Okay, people, so hope this question is clear. With that, we complete today's session. So I'll send you the notes and recording by tomorrow. So you can go through this before day after tomorrow's lecture, and that way you'll be prepared for the upcoming DPT also. Many of you have been asking about the syllabus and that and all that. So if you just prepare up to today's lecture's questions and concentrate more on, yeah, Bhargav, you have some question, beta?
Sir, what is that final answer which you have done in that last one?
Okay, I'll just share it. Yes. Yeah, so the final answer is square root of 8 by 5 GH. You know, because see this term here will become 5 by 4 into half. So half VA square into this bracket will be 5 by 4 is equal to GH. So take it to the other side and it will become like this. Is it clear now, Bhargav?
Yes, sir, getting it.
And I think I had given the value of H as 20 meters and G is 10 meters per second square. So you can just substitute, you will get the numerical answer. And VB will be 1/4 of that because we have already established this ratio, the momentum conservation. Right. So I'll make sure to send the recording and this thing notes by tomorrow. So make sure you revise the questions we've done today and in the last 3-4 lectures, the center of mass questions that we've done. So you should be all right for the DPT coming up on Sunday. Okay. That's it for today's session. People, wish you all the best.
Thank you, sir. Bye, sir.
Okay, bye, people.